Alright, here are two questions for today. You don't have to do them. You can sign in and just say, for attendance purposes, I looked at this problem. These are full-on grade 12 Newton's Law problems. If you can successfully even get part way through these problems, you are totally good for grade 12 Newton's Law. Alright? Why am I going into such detail in this kind of stuff? Because we don't have labs. Our lack of labs, instead of drilling you incessantly over again on the same questions, I figure I will help lift you up. So the lack of labs, you're getting something else in its replacement, and that will be as thorough of a job as I can to make up for the short course. So if you're overwhelmed, don't bother, just sign in and say I will here. So this first one, yes, I'm making fun of Gwyneth Paltrow. Sue me. I'm just not that impressed by her pseudoscience. So anyway, she gets on board this elevator. She weighs 54 kilograms. I looked it up. And the tension in the elevator cable is 1,058.4 newtons up. Then there's her mass. This is her special butterfly candy floss elevator she got from Willy Wonka. So the elevator has no mass. When she takes off, she is going to see the scale go to double her ordinary weight. So instead of saying 54 kilograms, it's going to read 108, and she's going to lose it and come completely unglued at the seams and go crazy. So you got to save her before she starts taking her own goop products as medicine. Can you explain, using Newton's law, why that bathroom scale is going to read double under the conditions I've set up? And the trick is to try to figure out what is actually lifting you when you're in an elevator. You've got all these separate forces, but ultimately what part of this system is actually attached to you and pushing you upwards? And that is the hint. You may contact me for more. Now, the unfortunate Inuit is another classic grade 12 problem. Methuselah Ernout, he was a guy I met in Iqaluit years ago, has two sled dogs, Sakari and Takani. And unfortunately, they go over a cliff, which is why it's the unfortunate Inuit. So he's trying to save his two dogs, right? Sakari, who's 20 kilograms, and Takani is 25. And the whole sled with Methuselah is 200 kilograms on a frictional coefficient of 0.01. So the question is, will the sled have enough friction to stay put, or will it start accelerating over the edge? So we turn it into a free body diagram of the sled, Sakari, and Takani. Now, I've already set you up with this before with a car with an engine and another car over the cliff. Now, I've just added a little bit of complexity, but it's really the same problem, except the force on the sled isn't from an engine, it's from friction. So here is how you set up a multi-body problem if you want to tackle some grade 12. First of all, the only thing pulling the sled forward is the gravity from the two dogs. So you can merge the two dogs together as a single mass. And the friction has nothing to do with the dogs. It is strictly to do with that sled and Methuselah on it. So friction is pulling to the left. Now you're confused because there's a bend in these forces, but that doesn't matter. The rope is basically making these forces straight line. I know it's dragging over the cliff edge, but we'll just assume there is no catching of the rope, that there's a pulley there. We have to make a bit of an ideal situation in physics, and then we add to that ideal situation later. So ultimately, this is really a two-force problem. If you look on the far right, you've got two masses of dogs. That created the gravitational force down, and really the opposite force is pulling straight up, is friction. Because all a pulley or a rope does is it redirects in any direction you want, right? You could play tug-of-war with other people and actually have teams parallel to each and just wrap the tug-of-war rope around a telephone pole and come back. You could take a tug-of-war rope, wrap it around a telephone pole, up a pulley to the second floor of a school. You can weave the rope any way you want. It's still a straight line problem. So we have two forces. The force of friction that was on going upwards now, the force created by the two dogs hanging down below, and what's the acceleration of the city? Tying together mass subject to two forces, and bingo, into exactly what I put on the last assignment. I'm going to try this. Now, in more advanced, no more than this in grade 12.
Guarantee you wouldn't see a problem than this. Is could you work out which force is on that at all locations? And there are really only forces on the system, so I set out. We have the force of friction on the sled, and we have the force of gravity onto Connie. Those are the only two forces that are not tied onto something else. Okay? Those are isolated forces, right? Now, obviously, the force of gravity onto Connie weaves its way through the rope, and obviously Methuselah can feel the weight of his poor struggling dog. But where are there other forces? Well, because I've moved these guys apart so you can see better, these two forces here, the tension between Sakari and Takani, there's only one force there, right? It looks like when I broke the rope that there's two, but there's really one, because Sakari's rope is pulling up on Takani, and Takani is pulling down on Sakari. They're equal and opposite forces. And that's true as well where the rope goes over the edge. If Sakari's rope is pulling down with 100 newtons, then the rope is also pulling up with 100 newtons. So these pair of forces here, you're not calculating 1, 2, 3, 4, 5, 6 forces. You're counting two isolated forces and pairs. These are pairs because these are the equal and opposite forces. So when you start calculating tensions in a cord, there's no in the tension here to here. You can consider a rope to be a chain of monkeys. The force just replicates itself down the chain. So once you calculate tension in any part of a rope, that's the tension for the entire rope. And that's where we go in grade 12. So can you figure out which of these ropes are pulled on the most? Now let's go back to this situation. I think you can figure this one out. If they're the ropes tying the dogs to the sled, where is the rope most likely going to break? Would it break here, between the dogs, or the spare rope hanging below Takani? Common sense. Where will the rope be under the greatest tension and snap first? Now, if you calculate these separate forces on Takani, you'll know you're right, because when you calculate Takani's acceleration as if he was just hanging there between two mystery forces in the fog, you will get the same acceleration you got here. And if you can solve this one, you have done a full-fledged end of unit grade 12 free body diagram. And if you're overwhelmed, forget about it. Wait till next year when you're ready. Okay? So that's your daily question for